Hello, hello, hello. This is Nicholas on this lovely Friday evening after a nice long nap. And now that I have done my Viva Voce, which is Latin for living breath, I would like to essentially give that same Viva Voce to you all. And so the Viva Voce is something that I have to do as part of my high school requirement to graduate. And it is basically where I've taken about a 20-page extended essay on a math topic that I've chosen and given basically an oral presentation of that paper, which I wish was something that was done more often in terms of these really large papers, because I feel like it's just much easier to understand. And so I wanted to do that to you all. I wanted to give you my Viva Voce. Now, my actual paper is general. Well, first of all, you have to be familiar already with what's known as the Shoelace Theorem. So the Shoelace Theorem is really nifty. Comes up a lot in competition math, especially, where say you've got this figure, this not symmetrical or just this weird kind of yucky figure here with four vertices, and you know what its four vertices are. Say they're x sub 1, y sub 1. Actually, let me write it up here. X sub 1, y sub 1, x sub 2, y sub 2, and two more, x sub 3, y sub 3, x sub 4, y sub 4. Going around like that in a clockwise direction. And so what the Shoelace Theorem tells you is that the area, so the area A is going to be equal to 1/2 times, and now we're essentially going to make a shoelace, first from left to right, and then from right to left. And it's going to be 1/2 times basically the product of the difference of each of those shoelaces. So it's going to be 1/2 times. Now here is the first shoelace in red. Maybe I'll put it in red here. The first shoelace is found by multiplying and then adding. So it's x sub 1, y sub 2, plus x sub 2, y sub 3, plus x sub 3, y sub 4, plus x sub 4, y sub 1, minus y sub 1, x sub 2, plus y sub 2, x sub 3, plus y sub 3, x sub 4, plus y sub 4, x sub 1. So for this part here of the shoelace, I've taken the product of each of these diagonals, and then notice also for x sub 4, I kind of loop back around to the top one here. And then for this part, I've taken the shoelace of these diagonals. So it's a really nifty way to find the area of a simple closed, each side is a line segment type figure where all you have to do is know the coordinate points. It comes up almost always in some form or another in competition math as well. Now, what I wanted to do was essentially generalize this from any figure here with just line segments as sides to any what's known as a simple enclosed curve. And so what I mean by a simple closed curve, well, if something's simple, that means that it doesn't intersect itself. So for example, a curve is, that's not really quite a circle, but maybe an ellipse is simple, whereas a infinity symbol is not. It's self-intersecting, it's non-simple. And then closed means it has a definite boundary, and obviously we need that to talk about area in any sort of a meaningful way. So when I go into more detail in terms of multivariable calculus, This circle here for sure is simple. It doesn't intersect itself enclosed. It has a definite boundary, right? This is its boundary. And we'll usually denote that later on as delta r. And if you're familiar with multivariable calc at all, this is the symbol for the partial derivative. We just also happen to call it the boundary. We use it for the boundary as well. So where would I like to start in generalizing any simple closed curve? Well, what I would like to do is, if we're talking about area, the first place to start, I feel, is with single variable integrals. So recall that in terms of a Riemann sum, the integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x. And so the integral is in essence just the limit of a Riemann sum. Now, let's say we want to generalize this. Okay, well, one other thing that's important to note is that the integral, do it like that, of a two-dimensional function, right? This lives in 2D space, say something like that, is found by first giving the bounds of a 1D space, right? So we wish to find the area, which is a 2D thing, over this line segment right here, which is a 1D thing. And so naturally, if we generalize to a double integral, then that means we would want to be finding, and I'll draw it here in 3D, or attempt to anyways. Say we have this like sheet right here or something. And then its projection onto the xy plane. Then we would be finding the volume, right? The volume of this whole thing, given this area or this region R that we input into the double integral. So it turns out, for all the same reasons as the single integral, that the double integral over the region R, for now is how I'll notate it, and now it has to be f of x comma y dA. So dA is dx dy or dy dx. It's the infinitesimal area component, just like how dx was the infinitesimal length component. So double integral over r of f of x y dA is given by, it's a double limit now, so lim as m approaches infinity, as n approaches infinity, and now it's a double sum from j equals 1 to m, I equals 1 to n of f of x sub I, y sub j, delta x, delta y. And so this might seem somewhat intimidating at first, but just realize that it's saying the same sort of deal. Here, if you look at just the limit as n approaches infinity part and that sum that goes along with it, so this and the delta x, you have all of the pieces for the single variable integral. So in other words, you've taken area along the x direction, and we approximate that area with rectangular prisms, just like how we did with rectangles in a single variable integral. And then if you apply that definition again using the limit as n approaches infinity, this sum and that delta y, then you have all the necessary things for that single variable integral definition again, but now you're sweeping along the y direction. Now, of course, it doesn't matter whether I first sweep along the x direction with rectangular prisms and then along the y direction, or if I first sweep along the y direction and then along the x direction. Either way, I'm getting the same area, I'm getting the same volume over that region R, right? The volume's constant, so it doesn't matter whether I did delta y, delta x here, but if I chose to first go along y and then along x, then I would have to flip-flop these two limits and then flip-flop these two sums because they would be still having to be written in the corresponding order. So the fact that you can say that, assuming that, of course, this bivariate function f of x, y is continuous, you can usually, if it's continuous, you can say that the double integral from y equals c to y equals d, x equals a to x equals b of f of x, y, and now it would have to be written as dx dy, is equal to also the double integral from x equals a to x equals b, y equals c to y equals d of f of x, y, dy dx. And this fact here is known as Fubini's theorem. And in essence, it says that if you've got this continuous function f, we can flip-flop the order in which we integrate, right? We're still going to get the same volume either way. But notice the order in which I wrote dx dy or dy dx is consistent in which the order I wrote my bounds of integration, right? So if y is my outermost integral, then dy needs to be on the outermost spot. And if x is innermost, then it needs to be innermost here as well. Okay, and now that I have the double integral, oh, also one other thing that you'll normally see is that the region R, if it's a rectangular region, you'll see R sometimes. So like, say we're in the coordinate plane, and now let me draw it here. If we've got like a rectangular region R, a rectangular region R, there we go. And let's say that this is x x equals a, or let's just call this the point a comma c, and then the point here b comma d. Then we would say that, and this is the region R, then we would say that R can be written as, well, x runs from a to b, right, along here. And then what we use is what's called a Cartesian cross product, and y runs from c to d. So the Cartesian cross product just means taking the union of where x runs and where y runs, and then defining the region that is swept between those two x and y's, which is this rectangle in this case. And so it's very common to see your bounds written like that. Now, the next thing that you would need is to note that, well, okay, for a simple solid, right, we have that volume is cross-sectional area times height. Base times height, the area of the base times the height, or cross-sectional area times height. So area then is, area is volume over height, but volume is just that double integral, right? It's the double integral over R of f of x, y, dA, divided by the height. Well, the height is the functional value at that point, f of x, y. But since the double integral is just a Riemann sum, and each term in the sum is going to have that factor of f of x naught comma y naught, in other words, at the point in which you're approximating your rectangular prism, and we're dividing by that same factor on the bottom here, we can just cancel it out. And so we have the double integral over R of 1 dA. So area is just the double integral of 1 dA, which is a super cool fact. And you can use that in and of itself to compute the area of a figure, but it doesn't quite go all the way in terms of the Shoelace theorem, because you need to know the parameterization or some form of writing down the figure in Cartesian or polar or what have you. And so it does require more information, but though this is a pretty powerful formula right here. Now, before I go into the all the kind of robust math in terms of generalizing the Shoelace theorem formally, quick and dirty, how you can do it super informally but very intuitively is, so if you think of it in terms of linear algebra in essence, so let's say that we've got a curve, a simple closed curve. I used a circle before, so let's use a circle. And if I approximate it, essentially using, quote, like a Riemann sum of triangles. And so what I can do is say, let's say I parameterize the circle here in terms of t, so that I only have one independent variable, right? That's the whole idea of parameterization. You can reduce the number of independent variables you have. So that means that, let's say, I start here and I go, let's say this is the point x of t, y of t, and then let's say I go just a little nudge more, x of t plus, say, dx, and y of t plus dy. And so now, if I do that, then I've generated like if this is the center here, I've generated a triangle. If I find the sum of the areas of all of these triangles here, then that's going to give me the area of the whole circle. And so the area of the triangle, if you know anything about determinants or have watched any of my videos or through Blue and Brown's videos maybe, the area of this triangle right here is 1/2 times the determinant of the matrix formed by each of these 2 points. So x, I'll just write, okay, I'll do it. X of t, y of t, x of t plus dx, and y of t plus dy. So the determinant here gives the area of the parallelogram spanned by these 2 points, which we can treat as vectors, and then multiplying it by 1/2 gives then the area of the triangle, since there's 2 triangles in that parallelogram. And I'll also notice by Gaussian row operations that I can subtract this, I can add or subtract the same thing to an entire row of a matrix, and so that's what I'm going to do. I'm going to subtract, no, I won't do that. Okay, I'll just do it kind of the longer way. So 1/2 times now x of t, y of t plus x of t dy minus y of t, x of t plus y minus y of t dx. And so now this and this will cancel, and you get 1/2 x of t dy minus y of t dx. And if I want to find the areas of all of those triangles, then all I need to do is just integrate. And that integration will happen, say, from t equals a to t equals b, our starting time, to our ending time. And what we'll normally do is draw a circle through here to say that it's what's known as a line integral over a simple closed curve. And this is actually all that you need right here. But it's not really rigorous at all, and so my paper was on actually making this airtight, so to say. Also, one other thing that you'll normally see, because this is a slightly misleading form, you'll sometimes see it as the line integral of x of t dy dt minus y of t dx dt, so that you can cement the dependence on parameterization, why that's necessary. So now, given that now we see what we're actually going for, we're going for this right here, I'm going to actually derive it rigorously now in terms of multivariable calculus. So I mentioned the term line integral, but didn't quite fully define it, and so that's what I'm going to do now. So let's say we're in 3D. We've got, say, a paraboloid in 3D. So maybe that's like one of its elliptical cross sections, and then, okay, and then it goes down like that, and then maybe I'll draw one more cross section here. So you see the idea that this is essentially a 3D parabola. And now let's say I take a path along the surface of this paraboloid, and then its projection onto the xy plane. So I have something like that. And now if I just kind of draw out this curtain here, it looks like a curtain, then it would look like, look like that. And so what the line integral seeks to do is find this curtain area. And so notice, though, that it is an area fundamentally that we're talking about, not a volume. And so it is just going to be, the line integral is just a type of single integral. But now it is going to have to be different, though, in that we require parameterization, because this is in 3D. And when we're in 3D, we would have a bivariate function. But we need to reduce the number of variables from 2 to 1, because we are only using a single integral. We're only going over a 1D input space. And so what we're going to do, and often this is the hardest part, is actually finding this parameterization. But we're going to assume that this curve right here can be expressed in terms of a vector function parameterization. So we're going to call this vector function. So we plug in a point, it gives us a direction to go. And then that's how we generate this curve right here. It can be vector parameterized. So say it's r of t, and each component is a separate function, x of t, y of t. And so now what we need to do is find the area of this curtain. And so we do it kind of the same way as the single and double integrals. What we're going to do is kind of create these rectangular prisms here. Or I'm sorry, just rectangles, and approximate the area of this curtain. Now, of course, it's just an approximation, and again, as we use more and more rectangles along this curtain, we're going to get a better and better approximation. So if I call the area of the ith rectangle a sub I, then the exact area A is the limit, as n approaches infinity, of the sum from I equals 1 to n of a sub I. So in other words, divide this up into more and more rectangles and sum each of those individual areas, and you're going to get the total area. So now a sub I is base times height, right? It's a rectangle. But so what is the base? Well, the base is the distance in between, say, 2 points. So say like this point and this point that form the bottom of the rectangle. So let's call that point. I'm actually going to write it down here because it's going to get kind of messy. X of t sub I m minus x of t sub I minus 1 times the height now. Or I'm sorry, that's just the it's the distance between those 2 points. It's the distance between the point x of t sub I minus 1 and x of t sub I, and oh my gosh, sorry, and x of t sub I minus 1 and y of t sub I minus 1, and x of t sub I, comma, y of t sub I. So it's just the distance in between these 2 points that gives us the base of our rectangle, multiplied by the height, which is f of x of t sub I, or comma y of t sub I. And the distance then, well, okay, we have f of x of t sub I, comma y of t sub I, times the distance, which is a big square root of x of t sub I minus x of t sub I minus 1 squared plus y of t sub I minus y of t sub I minus 1 squared, cylinder, that's square root. And now what I can do is, see, if this were just one term instead of two, it would be a lot nicer. But it is true by the mean value theorem that there exists a t sub I star such that x prime of t sub I star is equal to x of t sub I minus x of t sub I minus 1 over t sub I minus t sub I minus 1, which is delta t. So whenever I see this quantity of x of t sub I minus x of t sub I minus 1 right here, I'm almost always going to use the mean value theorem, multiply by that delta t, and then I can replace it and have a monomial under the square root, which will be a lot nicer. So f of x of t sub I, comma y of t sub I, multiplied by now, well, I'm going to probably put the delta t out of side of the square root because delta t squared would be a common factor, so I take the square root. And so we would have x prime of t sub I star squared plus y prime of t sub I maybe star. So using the same thing with the y's, but it's not necessarily the same time, so I just added an extra star. But now if this is a sub I, then that means that a, the exact area, is what we call the line integral over c of f ds. That ds is with respect to arc length, which is equal to the integral, still the line integral from a to b of f of r of t. Right, that's this part right here, because x of t comma y of t is r of t. That's what we said up here. And then now that's f of r of t times just the magnitude of r prime of t dt. And so this is the line integral over a surface path of a 3D function right here. Now, the next thing that kind of comes up, though, is when we're talking about line integrals over, not instead of over paths of surfaces, but over vector fields. Now, the fundamental idea about a vector field is it's a function f, and what it does is that you input a vector and you get out a vector. So it's a f that takes Rn to Rn. So it kind of synthesizes what we've done before. We've done like multivariable scalar functions that take Rn to R, and we've done some other types of functions where we take f takes R to Rn. And so the vector function is, the vector field is just a more general way, keeping the number of dimensions on the input space and the output space the same. Now, if we're talking about areas, though, we're going to be assuming that n is equal to 2. And so we'll write f in the form f, and that's equal to p of x comma y, because it's in R2, and then q of x comma y. So, for example, a vector field might look something like, this is actually kind of a cool one, where the vectors form like concentric circles. So something like that. And then, you would have the same thing. So like concentric circles. So I'm plugging in a point, and then I'm plugging in a vector, and I'm getting out a vector. And those vectors all together form a whole field of vectors along the plane. Now, let's say if we have this path that we wish to travel along the vector field, and let's say it's a particle traveling on this path. Let's say it starts at A and it ends at B up here. Well, okay, if the particle starts at A and it ends at B, right? Then so in between, where's a good place to talk about it here? Okay, well, if we start at A, right? The vector field looks like it's kind of going like this, the vector, and so it's kind of going perpendicular to the path, so it's not going to influence really how much work the particle has to do in order to travel along that path. Whereas something like right here, right, the vector field is pushing basically straight against it, and so more work is going to be needed in order to overcome the force of the vector field. But the important thing to note, though, is that at every instant, the work needing to be done by the particle to go from point A to point B is changing, right? At every instant, it's changing. And so the line integral over a vector field would represent the total amount of work that is needed to be done to go from, say, time A to time B. So recall, though, that work is a dot product between force and distance from physics. So basically, we have a force vector and we have a displacement vector, a distance vector. And so a component of the force vector that lies in the distance in which you want to go is the part that counts when you're talking about doing work. So the total, the work exactly would be given by the limit as n approaches infinity of the sum from I equals 1 to n of W sub I. And W sub I, you could say, as the work done on the ith subinterval. So if we were to split this curve up, right, into smaller and smaller intervals of time, and then take the work done on that particular interval and then sum each of those individual works, then we're going to get the total work. And the more subintervals we divide it into, the better our approximation is. That's the whole premise here. And so now we need to find what W sub I is. Well, W sub I is the force. So in other words, how the vectors are exerting newtons on this particle traveling along this vector field. So it's just going to be then f of x of t sub I comma y of t sub I. And now the second part, the distance, well, the distance is just going to be and actually what I'll do instead is I'll just call this r of t sub I, and I'm going to dot it with the distance. The distance is r of t sub I minus r of t sub I minus 1. And so now I have this kind of special quantity here again, and so I can use the mean value theorem. So work is f of r of t sub I times r prime of t sub I star times delta t. And so that would imply that the exact work W would be given by the line integral still, but over a vector field, it would be the integral from, say, time A to time B of f of r of t times r prime of t dt, which we sometimes conveniently write as the line integral, say, just over a general region C of f dot dr. So the dr is this r prime of t dt. Just, I guess, for ease of notation. And now notice that this form is pretty similar, though just a little different, right? Over a vector field, we have this. Over a surface, we have this. So here we're taking the actual magnitude, and we just have of a normal scalar function, multivariable scalar function, but here we're not taking the magnitude of r prime of t, and it's a vector function right here that we're talking about. Now, when we said before that f, since we're talking about in terms of the Shoelace theorem, it's going to be written as p comma q, where p and q are their own functions of themselves. And so that means that f dot dr is the same thing as still the line integral over c of p comma q dotted with dx dt dy dt, but then still multiplied by dt because dr is r prime of t dt, which matches up with this right here. So you would also see it sometimes written as the line integral over c of p dx plus q dy. Although this is a little misleading because you don't, well, one, you don't see any t's anywhere, right? And this is all about t, so sometimes also you'll see it written as you divide by a dt, then multiply by a dt up here, just to emphasize that dt is actually there. Now, I can actually tie line integrals and double integrals together now using what's known as Green's theorem, a special case of a more general Stokes theorem. So it might seem a little arbitrary at first, but if you do some more investigation into this on the Stokes theorem, you'll find that it's just a special case. So what I can do now is, see, we talked about the idea of a simple closed curve. And now one thing I didn't mention was the idea of orientation, whether something's positively oriented or negatively oriented. So we said, like I used a circle, I kept going back to a circle as an example. So it has a definite boundary. That boundary we usually call delta r. So that's the circumference of the circle. And it's also what we call positively oriented, because if I were to imagine traveling along this curve here anti-clockwise, then the actual region itself, r, right, travel along it, the actual region r is always on my left. So if you imagine yourself walking along the circumference and you look to your left, you would see the region r, the actual inside of the circle. So Green's theorem says that if we have a piecewise smooth, another thing, a piecewise smooth being that I can split the curve up into an infinite amount, or into a finite amount of piecewise continuous functions, and it's positively oriented, it's simple and closed, all these assumptions, then it says that the line integral over that simple closed curve, and I'll usually I'll denote that by drawing a little circle here, on the boundary of r, of p dx plus q dy is equal to the double integral over the region itself, r, of the partial of q with respect to x minus the partial of p with respect to y, dA. And now actually going about proving this, if I can prove the case where r is written as the locus of points x comma y, such that say that x is such that x is basically sandwiched between two functions and y is sandwiched between two other functions. So let's say f sub 1 of y is greater than or equal to x, which is greater than or equal to f sub 2 of y, comma, and we could say that y is sandwiched between g sub 1 of x and g sub 2 of x. So if I can prove this, if I can prove Green's theorem in this case of the region being written like this, then I can prove it in general because any region can be written as the smaller limit of this particular type of region. So let's first consider the even simpler type of region where R is the set of points x comma y such that f sub 1 of x is between, or y is between f sub 1 of x and f sub 2 of x, and x itself is just between say A and B. So in other words, we would have something like, say, like this. So x equals A, x equals B, and then let's say that this kind of curvy thing here is f sub 1 of x, and then this is f sub, actually, I don't want to make you think that they're identical, so this is f sub 2 of x. So f sub 1 of x and f sub 2 of x. And now this is also x equals A and x equals B. So if I take the line integral over the boundary of this whole region, so that would be over all of this, then I need to show that it's equal to that. And what I can do is, it would make sense that the line integral is a linear operator, meaning that I can split this boundary into 4 different boundaries, take the line integral over those, and then add them all together. So what I'm going to do is, if this whole thing is the region C, which is the boundary of R, right? If this whole inside thing is R, then C, and let's call this one C, this curve C sub 1, C sub 2, C sub 3, and C sub 4. Then C is the union of all these. C sub 1 union, C sub 2 union, C sub 3 union, C sub 4. And so now for C sub, we need to parameterize each of these. So for C sub 1, R sub 1 of t is just kind of a dummy parameterization. So we have t comma f sub 1 of t, where t ranges from A to B. C sub 2 now, so this was C sub 1, now this is C sub 2. So R sub 2 of t, well, x is always b, and then y just goes up this line, so let's, x is, I wrote x, I didn't write, instead of b, so x is always b, and then y is always linear, so let's just call that t, and then t ranges now from f sub 1 of b to f sub 2 of b. For c sub 3 now, R sub 3 of t is going to be, again, you're just traveling along f sub 2 of x, so that could be given by t comma f sub 2 of t. But now t ranges instead, and this is slight abuse of notation, say from b to a. So it doesn't really matter that I've written it incorrectly where I have a greater number and then to a smaller number, because this is just going to be bounds of an integral, and I can always just flip-flop the bounds and add in a negative sign in there. So it's fine how I've written it like this for the purposes of this video. And then now also, lastly, C sub 4. So we just did C sub 3, and then C sub 4 is that. Well, okay, x is always going to be A, so R sub 4 of t is equal to A comma t. And a little bit more of abusive notation. T is going to range from G sub 2, or I'm sorry, I don't know where I got G from. F sub 2 of A to F sub 1 of A. Right, it starts up here and it goes down there. Now, that would imply then that the double integral, and now if I just, let's just talk about this first part right here, or, well, it actually is the second part the way I've written it. But the negative of the partial of p with respect to y, dA, So the double integral over the region R of the negative of the partial of p with respect to y dA is the double integral. So x goes from a to b, and y goes from g sub, or I keep doing g, f sub 1 of x to f sub 2 of x of the negative of the partial of p with respect to y. Now it has to be written in dy dx because these are y equals f sub 1 of x to y equals f sub 2 of x, which is the double integral from a to b of now f sub 2 of x. I'm just flipping the bound so I can get rid of that negative sign, to f sub 1 of x, of now it's just the positive of the partial of p with respect to y dy dx. And now at this particular point, what can I do here? That's just going to be, if I'm taking the integral of the partial of p with respect to y dy, I'm just going to get p. So now I get rid of one integral, so I now just have from x equals a to x equals b a single integral of p of x comma g sub, I keep doing g, x comma f sub 1 of x minus p of x comma f sub 2 of x dx. And that's the same thing as if I were to just split this up and then go back to my parameter t. So the integral from a to b of p of x comma t comma g sub 1 of, oh my gosh, f sub 1 of t minus, actually I'll make it plus the integral from b to a of p of t comma f sub 2 of t dt dt. And now notice that this first integral here is what I would get. This first integral here is what I would get. It would be the line integral if I integrated over c sub 1. So if I took this and integrated over c sub 1, right? So t ranges from a to b, and we have p of r of t, but r of t is t comma f of t. So that's what I have right there. So that's just the line integral over c sub 1. And then likewise, this here is the line integral over c sub 3. Because in c sub 3, t ranges from b to a, like how I have written, and it's p of r sub 3 of t, which is t comma f sub 2 of t, which is what I have right here. And so now the first integral is, we're basically just missing the part of the line integral, namely the line integral over c sub 2 plus c sub 4 of p dx. But we can, that's just 0, because no matter what the actual region is, these two regions have the exact same parameterization, except one starts at b and one starts at a, and they go in exact opposite directions. So the line integral over them then will be 0, meaning that the line integral over the boundary of R, or in other words, c sub 1 plus c sub 2 plus c sub 3 plus c sub 4, the total boundary of p dx is the same thing as just doing the line integral of p dx over the whole thing, right? So that means that if we were to do the exact same logic, right, in the case where the region is being able to be expressed like this, and we were to instead compute then the double integral over R of the partial of q with respect to x dA, then we would find that that's equal to the line integral over the boundary of R, q dy. And then so their sum is nothing but what we have right here for Green's theorem, right? Because we had a negative sign here, and if we sum those, the line integral over the boundary of R of p dx and the line integral over the boundary of R of q dy, then we get this part gives us this part, and then this part gives us that part right there when we add the two together. And so Green's theorem is proven. Now, if we want to talk about areas, well, area is, it's equal to a number of things we found. It's equal to the double integral over R of 1 dA. It's equal to the double integral over R of the partial of q with respect to x minus the partial of p with respect to y dA. And it's equal to the line integral over the boundary of R, p dx plus q dy. And so now, if I want this double integral here to match this double integral here, I want to find a vector function such that the partial of q with respect to x minus the partial of p with respect to y is equal to 1. So what vector function f has that property? Well, if the vector function actually is negative y over 2 comma x over 2, it would work, because the partial of q, which is that second part with respect to x, is a half, minus the partial of p with respect to y. Partial of p with respect to y is minus negative 1/2, which is 1. And now you might say, well, there's an infinite amount of vector functions that satisfy that property for p and q. Yes, this is just the most widely used one. So then that tells us that area, if we plug this vector function into here, is equal to the line integral over this simple closed curve on the boundary of R of p, which is negative y over 2 dx, plus q, which is x over 2 dy. And so in other words, that's 1/2 line integral boundary of R of x dy minus y dx. and right here is exactly what we have way up here. X dy minus y dx. Now, I slugged through 3 pages of multivariable calc to get to it, but the whole idea, though, was that by doing it this way, one, you showcase a lot of the cool parts of multivariable, integral type calculus, and also, you get to explore Green's theorem, you get to explore line integrals, all that sort of stuff. So, if you know this formula and you're able to parameterize your curve in terms of another variable t, if you just take the line integral over the boundary, right, and usually the boundary is what's often hardest to set up, then you can just find the area of any simple closed curve. And in fact, to generalize even more, let's say it's not simple. Let's say it's still closed. Obviously, it has to be closed. Talk about area in meaningful ways. But let's say you want to, maybe you want to find the area of this infinity symbol. Well, if you go anti-clockwise and travel along it, right? At this particular spot right here, it's positively oriented because if I travel along it, the region is on my left. And at this particular spot right here, it's actually negatively oriented because the region does not lie on my left, right? That's the outside. But if I take, if I basically split the line integral up into finding the area of the positively oriented part and the area of the negatively oriented part, then the total area is the area of the positively oriented part, which I'll write with a sub plus, and then it's just minus the area of the negative oriented part, because this is going to, if you take the line integral over this, it's going to give you the actual area, just the wrong sign because it's the wrong orientation. But so if you subtract, you get a double negative, and therefore you get a positive. And so this generalization works for any curve with a definite boundary, simple or not. I really hope that you, if you're watching this far, that you found this video helpful and maybe even learned some multivariable calculus along the way. So with that,